In our previous lesson, we established a mathematical certainty. The greedy algorithm will always find the absolute optimal solution for the fractional knapsack problem. It succeeds because the dataset models a continuous physical reality. When dealing with resources like gold dust or liquid, the algorithm can slice the final item into the exact fraction needed to perfectly optimize the available space, leaving zero gaps. It executes this perfect packing process with extreme computational efficiency, operating at O(n) log n complexity. If this approach is mathematically flawless and highly efficient, why do we discard it for certain variations of the exact same problem? The answer comes down to a shift in physical constraints. In the real world and in computing, not every resource can be infinitely divided. Think of a laptop, a mobile phone, or a server rack. You cannot pack half a laptop. These are discrete, rigid objects. This creates a strict binary environment. Mathematically, every item now forces a choice. 1, meaning you take the entire item, or 0, meaning you leave it completely behind. This is the 0-1 knapsack problem. We are going to test whether the efficient logic of the greedy algorithm can survive this rigid boundary. Changing the rule of divisibility transforms a simple packing task into a combinatorial problem, where the most attractive local choice can create a permanent spatial penalty. This diagram establishes the strict parameters of our test environment. We have a knapsack with a hard capacity limit of exactly 50 units. We populate our first variable, item A. It weighs 10 units and offers a profit of 60. We add 2 more variables. Item B weighs 20 units with a profit of 100. Item C weighs 30 units, bringing a profit of 120. The greedy strategy demands we calculate the profit-to-weight ratio to identify which item packs the most value into the space. Item A yields a ratio of 6. Item B yields 5. Item C yields 4. The algorithm establishes its strict priority order: A, then B, then C. Sorting by maximum value density is the standard method for local optimization. The next sequence follows this logic exactly. Executing the first logical choice, the algorithm selects item A because it has the highest ratio. Our total profit registers at 60. Our remaining spatial capacity drops from 50 down to 40. The algorithm makes its second logical choice, selecting item B, the next highest ratio on the board. The profit counter climbs to 160. The remaining spatial capacity is now tightly constrained. We have exactly 20 units of space left. The algorithm attempts its final step, evaluating item C against the remaining space. Item C requires 30 units. We only have 20. Because we are in a 0-1 environment, taking 2/3 of item C is illegal. The item is entirely rejected. The algorithm terminates. The final profit remains 160. The algorithm reached a dead end with 20 units of empty space. Trapped by its own requirement for a 30-unit item it could no longer fit. To test if 160 is actually the highest possible value, we will construct an alternative combination on the right side of the screen. For this test, we deliberately ignore the highest ratio rule and skip item A entirely. Instead, we select item B, adding its weight of 20 and profit of 100 to the system. Then we select item C. Its weight of 30 perfectly complements the remaining 30 units of space. The capacity is maximized. The profit counter hits 220. Compare the two final states. By deviating from the greedy priority, we generated a profit of 220, decisively beating the greedy output of 160. Because a higher profit combination exists here, the greedy algorithm has officially failed the test of optimality. Why did choosing the most individually valuable item lead to a worse overall outcome? This failure happens because the greedy algorithm is myopic. It evaluates the immediate step and never models future consequences. By selecting item A first, the algorithm consumed 10 units of capacity that were needed to fit larger items later in the sequence. That single local optimization inadvertently blocked the globally superior combination of items B and C. To be clear, Greedy logic does not fail on every single 0-1 knapsack dataset, but because it fails on some, you cannot trust it to guarantee an optimal solution. In rigid, discrete data environments, unused space is the ultimate penalty, and greedy logic is completely blind to it. This comparison table isolates the rule of constraint. When division is perfect, greedy works. When items are indivisible, greedy fails. Because discrete items cannot be chopped up, algorithms must evaluate entire combinations simultaneously, rather than one by one. To solve the 0-1 knapsack optimally, we must abandon the greedy approach and use mapping techniques like dynamic programming or branch and bound. While greedy logic hit a hard ceiling here, it remains an effective tool when applied to the right physical constraints. In our next lesson, we will apply greedy principles to a massive, real-world data compression problem, building prefix codes using a Huffman tree. Effective algorithmic design requires matching the mathematical logic to the specific constraints of the data environment.